my first time in Russia too, so thank you. Okay, let us give me time to give few definitions just to fix the notation. So given a n-dimensional manifold M, and given m plus 1, the smooth vector fields of M, we can define what is an affine control system with drift. It is a family of dynamical systems parameterized by a m-dimensional vector in a slope set of Rm and Q. We will call little u the controls and dq the space of control parameter. This is an affine system because on this equation the controls appear in a affine way. And we have a drifter, that is an uncontrollable vector field of our system. Okay, we don't want to consider just constant control, but admissible control. We have infinite maps from a time interval to our space of control parameter u. And just for the ficta notation, we call the calligraphic Q the set of admissible control. And now we are able also to define what is an affine set, attainable set from Q0. So there are all the points in our manifold that can be attained from the point Q0 along the admissible trajectories that are defined by the solution of this system defined by the admissible controls. Okay. And then now we can define explicitly what is the optimal problem. Indeed, I'm going to study this problem. So, given a point Q0 in M, given a point in the attainable set from Q0, we look for term optimal controls that are admissible that define a term optimal control such that at time 0 we are in Q0 and at time 1 we are in Q1, and T1 is the minimum time as possible in which we can attain Q1. And and to have the existence of this term optimal trajectory, we need that our space of control parameters must be compact and convex, thanks to Filipov's theorem. Okay, so let's go to the main question of what I'm going to explain. We are going to consider the optimal problem in a three-dimensional manifold with a two-dimensional control. So we are considering our affine control system with drift, this one, with F0, F1, F2 smooth vector fields, and we are considering admissible controls with, in particular, which they take value in the disk, in a two-dimensional disk, this one. Okay. And what we want to study? We want to study what is the regularity of term optimal trajectories. Okay. From the definition of the system, it is sufficient to study the regularity of optimal controls. Okay. So, considering as a definition that a switching is a discontinuity of optimal control, it means that our optimal trajectory has a behavior and then change in a drastic way the direction. Okay, that is the switching point in which we have a discontinuity of the optimal control, and we want to understand how is the structure of these switchings. Okay, that's the meaning of the title of this seminar. We're studying switchings, this kind of phenomenon, in term optimal problem for the three-dimensional case in two-dimensional control. Okay. Now I would like to. Obviously it seems a particular case. Okay, but actually we are going to. We would like to see if we are the method that we are using. It seems that is useful to study the n-dimensional case for the codimension 1 control. Okay. And now let me give you previous results to understand more the motivation of why it's so interesting to study this problem. The first example that I want to show you is the Fuller phenomenon. Okay. In this example, we study optimal trajectory is in a real line that follows this system. Okay. So the second derivative of our trajectory is equal the control u that is in a bounded segment -1 plus 1, and we want to study optimal control that minimizes this cost. This problem can be studied as a term optimal problem, okay? And why is it interesting? Because if we consider in the real line optimal solution that starts to a point different than 0 and arrive in 0, okay? For this system, we have optimal solution that arrive in finite time at 0, okay? And the corresponding optimal control have this behavior. Then it is constant 1, and then has a discontinuity of the control, then it's constant -1, and so on. So as I defined you, that discontinuity of the control, we call it switching, and it is a drastically change of direction of our control. It means this is a particular case in which we have a convergent series of switchings. Okay, so we have a convergent series of discontinuities of our optimal control. This phenomenon is called shattering. Okay, and there's a common opinion that for a not very high dimension, this kind of phenomenon can be avoided with a perturbation of the system. Perturbation of the system means that we can consider general condition of the vector fields of the vector fields that define the system. What I want to show you is that in a two-dimensional case with scalar control, Ugo Boscani and Benedetto Piccoli gave the complete classification of optimal trajectory in this case, and in particular they observed that the optimal trajectories are piecewise smooth under general condition on the fields F and G. It means that in this case, switchings, okay, discontinuity of the optimal control are isolated. Okay, just with the perturbation of the system. And also we studied the two-dimensional case with scalar control by Andrea Androcciotto and Mario Singolotti, and they gave a similar result. And they saw that out of a one-dimensional satisfied subset in the three-dimensional manifold, it means that out of a particular subset, there is a common finite local bound on the number of arcs. So also in this case, we don't have chattering phenomenon. Okay. So that's why it's more clear how we study this problem that is still in the two-dimensional manifold, okay, but with two-dimensional control. And we wanted to find a generic condition such that also in this case our switchings are isolated. Okay. So good. So let me go deeply in how we study this problem. So from the Pontryagin maximum principle, that is a very important necessary condition of optimality of curves, we know that every optimal curve has an extrema, that is a lift in the cotangent bundle, okay, and we call it extrema, this lambda t. And we know that this extrema satisfies a Newtonian system, okay, and I want to show you what happened in this case. So in this case we can define n. This is a submanifold in the cotangent bundle. We call it singular locus, in which every point lambda that is a lift of Q, of point Q in M, we have that lambda is orthogonal to F1Q and F2Q. Okay? So with our notation HI lambda, that is lambda F1Q, we have that lambda belongs to M if and only if H1 lambda is equal 0 and in the same time H2 is equal 0. And we have that out of this singular locus, extremas satisfy the Newtonian system given by this Hamiltonian, okay? That is moved out of our singular locus, okay? And And so here we're defined all the extrema, okay? And then now we have that if we have optimal trajectory such that if they have an extrema that lies in this part of the tangent bundle, then they are smooth, okay? So right now, just now, from now we have already a characterization of the smoothness of optimal trajectory in this case. In particular, we have that optimal control are in this form, okay? So it means that they are in the boundary of the space of control parameter, okay? So what we can say that in this case, optimal trajectory are smooth and controls lie in the boundary of our U, so in this way. And they are also smooth. Good, so the main question now is to understand what happens if our extrema go through our singular locus, okay? We don't know at the moment, yes, and our result is about this. Indeed, we have found that given our fine control system, three-dimensional, in the three-dimensional case with two-dimensional control, assume that F1, F2 are everywhere linearly independent, and assuming that in a one point Q bar we have that the rank of F1 Q bar, F2 Q bar, the brackets, the drift F1 and the brackets F0, F2 in Q bar is equal to 3, then we have that in a neighborhood of FQ, of Q bar, any optimal trajectory is bend, okay, namely it's smooth, or is bend with an isolated switching. Bend means that the trajectory is a concatenation of bend arcs, okay? So in our cotangent bundle, it means that the corresponding extremum pass through the singular locus and immediately go out, okay? With respect the controls, what does it mean? It means that it is smooth, and then it has a discontinuity, it passes through the singular locus, so the denominator is equal to 0, and then from a point of the boundary, it arrives to another point of the boundary, okay? And we were also able to understand how is this jump of the control, okay? So let's go deeper to the statement. Indeed, given lambda bar, a point of a lift of our Q bar on our singular locus that is different than 0, we have that this condition is equivalent to this one. Indeed, from our notation in which Aj is lambda with brackets F5, Fj, Q, then this condition means that if we are considering lambda bar that is orthogonal to F1 Q bar, F2 Q bar, then we cannot have that also the bracket F0 F1 and the brackets F0 F2 at the point Q bar they cannot be also orthogonal to lambda bar. So we have this condition. Okay. And what else? If we consider this, we call it R square, okay? Let's notice that this it depends on the vector fields. We can define this condition that depends only on the choose on how we choose the vector fields. So we have two cases in which R square is strictly greater than H12 lambda bar square, or it is less equal than. Okay, and what we have seen, that if it is greater, strictly greater, then this is the case in which we can have a switching, in which we can have an extremum that passes transversely to the singular point, to the singular locus. And we also calculated exactly how is the jump of the control in the boundary, and from an angle of the circle theta minus to the angle theta plus. And in particular, I want to show you that this comes from the fact that theta minus minus phi phi is defined in this way, is something that is defined by the system, okay? So we have that the sine of these two angles, theta minus phi, theta plus minus phi, is this value defined explicitly from the system, h12 lambda bar over r. And what we can see, if h12 lambda bar is equal to 0, then the difference between the two angles, theta minus and theta plus, so the jump is the antipodal point of the boundary of the disk, okay? And these are the cases in which the Lie brackets of f1, f2 is equal to 0, okay? For example, also the linear case has this behavior. And if we have that this inequality come more and more like an equality, okay, it means that the angle, the jump, comes smaller and smaller, okay? So when this becomes an equality, we don't have no more a jump of the control. And we can say that in this case we don't have switching, and the control is almost everywhere and not in that point, continuous. And so we can say that our trajectory is C1. Okay, and in the yes, just because I wanted to show you that it is easy to calculate the jump. Okay, in the other case, if the inequality is equal or less, we have that optimal control is continuous and it's smooth if the inequality is strictly less. Okay, why? Because in this case, optimal to extremal in the tangent bundle doesn't pass on through the singular locus. Okay, so we are only in the case in which everything is smooth. What we have studied, we study also the flow of extrema that pass through this singular locus, and we observe that the trajectory are Lipschitzian, and the flow is continuous with respect to initial values, but not Lipschitz. Okay, this is the problem that we at this moment we cannot say that the extrema that pass through the singular locus are all optimal, because we know Pontryagin maximum principle gives only a necessary condition of optimality, not sufficient. So we know that if we have optimal trajectory in this neighborhood that has a switching, the switching must be like this. But we don't know that exactly the projection of the extrema that we have found is exactly optimal. We can prove optimality only in the linear case in which we have the uniqueness of the optimal trajectory. Okay, this is the end of the complete statement that we have proved, and I would like to show you the idea of the proof. First of all, I want to show you that given our condition, there are not singular arcs. And singular arcs are optimal arcs in which they have the extrema that lies in the singular locus. Okay? And why? Because if we have an extrema that in the time interval lies in n, then the time derivative of this condition must continues to be 0. And this is equal to these equations. Okay? And we can say that if h12 is equal to 0 in this case, if we don't have this part, we have a contradiction by the condition R star, red star that we have, that says that it's not possible that h01 and h02 in the same time are equal to 0. Okay? And if h12 is different than 0, in the case where we had switching, so in the case where we have this inequality 3 greater, we have a contradiction because we have a control that is out of our disk. And in the other case, that could be extrema on the singular locus, okay, but they are not optimal by the Gauss condition. So this is, and this result allows us to study directly the Hamiltonian system, okay? This the smooth Hamiltonian system from this Hamiltonian that is moved out of our singular locus, and we can study it in a neighborhood of a point of the singular locus in which the right-hand side of this Hamiltonian system is discontinuous. Okay, so at the end we are studying a dynamical system with a right-hand side discontinuous. And so let me give you technical details to show you how we study this problem. So we have a smart exchange of variables, and from lambda we consider locally the problem, so a neighborhood in a 3 times arbitrary power, and we consider these coordinates where h3 is just defined by the vector product of f1 of 2 that we are supposed to be linearly independent, and we consider the technique of blow-up, in which instead of a point in these coordinates x bar, we consider the polar coordinates with respect to the coordinates h1, h2 with rho and theta. I want to recall you that if h1 and h2 are both equal 0, we are in a singular locus, okay? So we are in a point of discontinuity of our new Hamiltonian system. And we are considering, so instead of a point, x bar as a circle with points in these circles that are x bar theta that are defined by the angle theta. So in this case, the Hamiltonian from this becomes this with rho, and as I want to recall you that our optimal control were just cosine theta and sine theta in these conditions. Okay, so now we can define explicitly the optimal control with respect to the behavior of the constant theta. And just for notation, we have this h theta that is just rho. Okay, so let us now see explicitly how is our Hamiltonian system. So we have this x dot part. We just we wrote f theta in a smart way, that is this. And I want to stress the fact that the system is discontinuous, and indeed we have here 1 over rho, and if rho is equal to 0, we are in the singular locus. Okay. And so just write explicitly this part, and I want to show you now how we gave the two conditions about the two inequalities that I had, and yes, so we are considering x bar and x bar theta, and I want to recall you that we defined r squared, this value, and we have rho and phi, L and phi, just defined by this by these two constants, and let us see that this part. Let us calculate this part in our little disk, in our little circle, okay? And we have just this formula, and this formula is equal to 0 if and only if the sign of this of theta minus phi is equal to h1 coulomb x bar over r. It was our old element. Indeed, now you can receive the condition that we gave. Okay. Indeed, if we have a strictly less inequality, then this value is always different than 0. And then, if there are the opposite strictly inequality, we have two angles, okay, where it is equal to 0, and obviously in the third case we have just one angle. And why I told you this? Because in this first case, we have indeed that considering the behavior of the coordinates rho, okay, we are arriving in the singular locus of our extreme, or if we arrive to rho equals 0, in this case rho t remains always different than 0. Okay, so in this case we are in the case in which everything is smooth, and we have seen that in this case where we have two angles, there is exactly one unique extrema through our singular point that arrives in out with angles theta 1 and theta 2. Okay, and this the equality case is the limit case in which we don't have theta 1 and theta 2 but just an angle. Okay, it's very difficult to understand how really this extremal in this case works, but as I told you, we can this is a limit case, so we don't have a switching in this case. I just want now to stress how we study this case in which we found an extrema that passed to the singular locus, and what we did we scale the time. We don't use no more the time t but the time s, such that the derivative with respect s of ts is rho s. So we rescale the time, and our whole system become this system that is that has no more a discontinuity point of the right hand side. Okay, and what we have rho, and this part, and so in rho equals 0, this is constant, this is constant, this is constant, and we saw that this part has two angles in which is equal 0. So these 2 points in this circle that we found become equilibria of this system. Okay, so we have equilibria of this system, and from the Societasvili theorem that says that locally in an equilibria, if we consider the eigenvalues of the Jacobians of the system, if we have the real part of the eigenvalues strictly positive or strictly negative, we have a behavior as a saddle. Okay, and then we have a central part. So from calculating the eigenvalues of the Jacobian of this system, we have this behavior here. And indeed, we can see that with the arrows, we come inside, we go, and then we come out with these 2 angles. Okay, so we found explicitly how does it work. And the uniqueness of the extrema that goes inside comes from the fact that rho equals 0, the submanifold, is invariant from this factor. And then another question was, do we arrive to this point in the whole time with finite time? Because we know that these are equilibrium for this time s, and so at time s we arrive to this point in infinite time. Okay. So our question was that do we arrive in finite time? And the answer is yes. So we find explicitly how is the extrema that arrive through this singular locus. And I don't know how we find in time, but yes. So this is the end. I'm here for every question, and thank you for the attention. I stop.
Are there some questions or remarks?
Yes.
Yes, so could you repeat the condition star or asterisk
Yes,
about the brackets?
Is this.
Yeah,
So
okay.
the rank of this is equal to.
Okay, so as far as I see, it roughly speaking corresponds to the case that the linearization is controllable at a point q bar.
No, it says.
Yes, yes.
Yeah.
And the question is it possible to do some construction under more general controllability condition? For instance, a particular case of Sussman's condition, if you also have the first order Lie bracket, but you take into account, say, the Lie bracket F1, F2.
Please.
If you take into account the Lie bracket F1, F2, is it possible to do some construction for this case as well? No, I mean in the run condition, you do not.
If I put also the fact that also we study
mean just if
Is that
you
enough?
replace, sorry, if you just replace the condition star with the condition when you put the lib bracket F1, F2.
Also in this one. So we have.
Or maybe instead of some brackets with F0, you take into account
We
that.
study also this case.
Okay.
But this condition is more take into account to more cases. In which in this case we have.
Easier to satisfy, yes.
Okay. Because you imagine the idea that the system made this small time locally controllable even for using first order lib bracket and a Q bar, but this is not guaranteed by the linear approximation, but this is guaranteed by F1, F2, say.
But here is a little bit different problem. Here we study not at zero, but we study time optimal problem. So it's not controllability story. It's perfectly controllable at zero, but we study optimal control. Control belongs to the boundary of the disk. It's not related directly to control.
Yeah, it's not related, but this is just a technical question. If you just use F1, F2 here, are we able to...
And this guy, I think it's possible.
It's possible.
But the behavior should be
Very good. More questions?
There was a phrase about linear systems.
Yes.
Three men.
Yes. We have. I was talking about the optimality of the extremal in this case.
What is linear case?
Linear case in this where the drift is just linear, a matrix plus x or times x, and f1, f2, the lib brackets is equal to 0, or they are constant as you know.
By the way, turning back to your condition, I expect that if at this point more than bracket are not linearly dependent, but F1 to dependent, then we will switch.
This was the first.
It's a too big this perturbation of the subdomain. In subdomain we do not have switch. Okay, we have the lift, but
So it will be bank case, not bank.
looks like that, yes, because for us, you know, because look at this condition here. If F1, F2
The previous one.
dominates, is bracket F1, F2 dominates bracket F0, F1, F0. Then we do not have switch. This is a part of the story.
Oh,
It
so
means that H1, 2 is bigger, and in the case you are interested, R is 0.
Okay.
What we do, for us it's crucial that R is not 0. But looking at this condition and remembering some remaining situation, we may expect that we do not claim that we do not have switch, but we may expect this kind of behaviors.
Well, so I'm not claiming that R is necessary 0, but you can imagine
No,
that
I feel it
some,
R is 0.
some artificial situation when...
No, if R is not 0, we
Yeah.
have total understanding. But if R is only our condition that R is positive. That star means that R is positive. Exactly.
Maybe not.
Equation star is equivalent to
it's
it
equivalent.
is written here.
And there's a three-dimensional manifold.
It's 3 dimensions.
You assume that F1 and F2 are very independent. Okay.
Oh yeah, that we also
Yeah.
see. That we also see. So it is reasonable to expect that if R is 0 but H1 of 2 not, we do not have switch. But we have to check. Because there was a question.
About 39.
Then the existence of switching.
Book?
Existence of switching in the
Ah,
case
yes,
of
yes,
R
yes.
0 but H1 2 not.
So, let us think. Okay.